The biggest megaprojects under construction in February 2026 are reshaping continents and entire economies. From record-breaking tunnels and next-generation rail links, these builds are racing against impossible timelines and brutal engineering challenges. Today, we track the most ambitious sites on the planet to show which projects are closest to completion and which could change the world first. Set about 40 kilometers east of Ho Chi Minh City in Dong Nai Province, Long Thanh International Airport is Vietnam's largest greenfield airport built, laid out on roughly 5,000 hectares of land. The master plan is phased. A first stage designed for about 25 million passengers per year and roughly 1.2 million tons of cargo per year, then successive expansions aiming toward an ultimate system capacity, often described in planning targets, at around 100 million passengers per year with multi-terminal, multi-runway operations. Phase 1 is the decisive leap from an empty site to a functioning airport. The airside core centers on a single long runway with associated taxiways, aprons, and aircraft stands, plus the first passenger terminal complex. On a project like Long Thanh H, early progress is measured in hidden work, ground improvement, deep foundations, stormwater canals, and buried utilities that must be finished before the airport can look vertical. By 2026, those enabling packages are expected to have largely matured into heavy structural construction and fit out. In February 2026, the construction focus typically shifted from raw earthworks to simultaneous airport systems work across dozens of zones. On the terminal, that means completing major concrete and steel frames, pushing the roof structure and cladding forward, and accelerating mechanical, electrical, and plumbing installation so interior spaces can move into partitions, ceilings, flooring, and architectural finishes. It also means installing long-lead airport equipment, baggage, handling conveyors and screening interfaces, escalators and lifts, check-in and gate infrastructure, and the early backbone of IT and security networks. On the runway and movement areas, February work commonly targets pavement layers and grading tolerances, with asphalt or concrete placement progressing in sequenced pours, followed by shoulder construction, drainage tie-ins, and service roads. Airfield electrical works become a parallel critical path. Duct banks, cable pulls, transformer pads, and preparation for approach lighting, runway edge lights, signage, and the control systems that bind them together. Supporting facilities, fire and rescue, maintenance zones, fuel storage and hydrant routes, water treatment, substations, and the air traffic control tower advance in step because commissioning can't begin until these utilities are stable. Across the rest of 2026, the project typically pivots from build to make it operational. That includes systems integration, power on, and resilience testing, calibration of navigation aids, trial operations inside the terminal, and progressive commissioning of baggage, security, and passenger processing. On Singapore's southwest coast, the Tuas Mega Port is being built as a single consolidated container hub, replacing and absorbing operations from multiple older city terminals into one deep water site. The full development is commonly described in 4 phases, expanding step by step until the port reaches an ultimate design capacity on the order of 65 million TEU per year, with completion targeted in the 2040s. The footprint stretches across a long reclaimed shoreline and newly engineered basins, where land formation, quay construction, and yard automation are planned as one integrated system rather than separate projects. Construction is organized around 3 physical layers: the marine interface, the container yard, and the inland connections. At the waterfront, the critical assets are kilometers of deep draft berths with massive quay walls, fender systems, and high-capacity crane rails designed to accept ultra-large container vessels. Behind that, the container yard is laid out for automated stacking, with dense blocks served by unmanned equipment routes, power distribution, and communications infrastructure. Inland, the port depends on highway connectors, gate complexes, and future logistics links that must handle high truck volumes while minimizing dwell time. By February 2026, Tuas is in the phase where the early operating sections are already functional, and the next expansion sections are being pushed from civil works into equipment and systems delivery. That means continued ground improvement and pavement works in new yard zones, plus installation of underground utilities, high voltage feeders, substations, fiber networks, stormwater systems, and firewater mains. Along the quay, February work typically includes additional caisson or diaphragm wall segments where new berth lengths are being created, followed by quay deck concreting, crane beam alignment, and corrosion protection work that must be finished before ship-to-shore cranes can be commissioned. The automation stack drives the construction schedule. Across 2026, the work is not just concrete and steel. It is also the controlled rollout of automated yard cranes, automated guided vehicles, or autonomous trucks, charging infrastructure, positioning beacons, and the software layers that coordinate container movements. In practical terms, that means building and testing dedicated vehicle lanes, sensor corridors, and fail-safe systems, then running progressively larger trial operations to validate throughput, safety separation, and recovery procedures. Operational buildings expand in parallel: gatehouses with multi-lane screening, maintenance depots for automated equipment, control rooms for yard orchestration, and security installations across the perimeter. Dredging and seabed protection remain ongoing, where basin depths and turning circles are refined for larger ships, with careful management of silt, slope stability, and navigational clearances. Between the Danish island of Lolland and Germany's island of Fehmarn, the Fehmarnbelt fixed link is being built as an immersed tunnel carrying both road and rail in a single structure. The main tunnel is about 18 kilometers long, planned with a 4-lane motorway and a double-track electrified railway, plus dedicated service and safety areas. In operational terms, the project is designed to replace a ferry crossing with a fixed connection that supports high-frequency passenger travel and heavy freight, while cutting the cross-strait journey to minutes rather than an hour-scale sailing. The construction method is industrialized. Large tunnel elements are manufactured on land, then transported by specialized vessels, lowered into a dredged trench on the seabed, aligned with millimeter control and connected underwater. Each element is sealed with gaskets and closure pores. Then the trench is backfilled and protected with rock and filter layers. The Megaproject part is not only the length, but the repeated precision of this cycle, performed dozens of times in open marine conditions while maintaining navigation and environmental controls. By February 2026, the work is concentrated in 3 synchronized fronts. First is element production in the dedicated casting factory at the Danish portal area, where reinforcement cages, formwork, concrete pours, curing, and waterproofing are managed like a shipyard assembly line. Second is marine preparation, including continued dredging and trench shaping along the alignment, placement of bedding layers, and installation of temporary markers and monitoring systems for settlement and scour. Third is portal and ramp construction on both shores, where cut and cover sections, approach structures, pumping systems, and transition slabs connect the immersed tunnel to the surface transport corridors. In February specifically, the project typically runs at continuous delivery pace, completing additional tunnel elements in the factory, outfitting elements with embedded service conduits and structural inserts, and staging them at a basin for float out. Offshore, crews focus on trench readiness and weather windows for immersion operations, including tug-assisted transport, controlled ballasting, and real-time surveying to lock each element into place. After placement, teams execute joint closure works, internal access checks, and begin early-stage fit-out, where sections are watertight and stable. Across the rest of 2026, the visible change is the lengthening of the submerged structure and the transition from marine works to interior systems. As more elements are connected, the project accelerates mechanical and electrical installation inside completed segments, ventilation ducts and fans, power distribution, lighting, emergency, communications, drainage, fire suppression interfaces, and monitoring sensors. Roadway build-up layers, rail trackbed works, and cable routes start to occupy the schedule once long continuous stretches become available for uninterrupted installation runs. From the banks of the Detroit River The Gordie Howe International Bridge is being delivered as a new, high-capacity road crossing linking Windsor, Ontario to Detroit, Michigan, designed to add redundancy and modern border processing to one of North America's busiest trade corridors. The signature structure is a cable-stayed bridge with a main span of about 853 meters, making it one of the longest cable-stayed spans in North America, and it carries 6 traffic lanes with a separated multi-use path for pedestrians and cyclists. The bridge is only one piece of a much larger construction package. On each side sits a purpose-built port of entry, laid out like an airport terminal for trucks and cars, with inspection plazas, secondary, screening areas, administration buildings, and secure circulation routes. The overall site work includes new interchanges and direct freeway connections, designed to keep commercial traffic moving without feeding congestion into local streets. This is why the project is measured not just in span length, but in the scale of earthworks, pavement, drainage, and security infrastructure across hundreds of acres. By February 2026, the physical bridge is expected to be in the final stretch. The pylons and deck structure largely complete, with work focused on finishing operations that turn a built bridge into a safe operating asset. That typically means continued installation of stay cable systems and final tension tuning where needed, completion of expansion joints, deck surfacing, barriers, lighting, and intelligent transportation systems. On a cable-stayed bridge, the last phase includes detailed alignment checks, load testing preparations, and final painting or protective coating. Touch-ups, because corrosion resistance is a life cycle requirement, not a cosmetic detail. The ports of entry become the schedule driver as opening approaches. In February, crews are usually pushing architectural and MEP completion inside inspection buildings, fitting out inspection booths, control rooms, and secure holding areas, and completing power, communications, and security networks. Yard paving and line marking progress in parallel, with drainage tie-ins, salt management features, and snow clearing logistics planned into the geometry because winter operability is non-negotiable at this latitude. Gate systems and screening technology require coordinated commissioning, so construction sequencing is often organized around areas available for systems integration, not just around concrete placement. Across the rest of 2026, the project emphasis shifts to end-to-end commissioning. Roadway approaches on both sides move through final asphalt lifts, signage, overhead gantries, and barrier installation, then into integrated ITS testing for speed management, incident detection, and lane control. For the bridge itself, the year includes final cable vibration mitigation checks, completion of the multi-use path finishes, and the certification and handover processes that rely on documentation as much as physical work. Stretching from Poland through Lithuania, Latvia, and Estonia toward Tallinn, Rail Baltica is being built as a new European standard gauge railway intended to replace the historical break of gauge constraint that has limited seamless north-south rail movement in the region. The mainline program is typically described as roughly 870 kilometers of new or upgraded corridor across the 3 Baltic states, designed for fast passenger services and high-capacity freight, with a broader system that includes terminals, intermodal yards, and urban station rebuilds. The mega-project complexity comes from doing 3 national builds as one interoperable railway. Track is only the visible layer. The full scope includes new embankments and cuttings, drainage and culverts across wetlands and agricultural land, grade-separated crossings, noise protection, traction power, and a digital signaling backbone designed to be consistent end-to-end. Key nodes include airport and city connections, border interfaces, and logistics terminals, intended to shift freight from road to rail with predictable transit times. By February 2026, the construction map is typically fragmented into many active contracts. In one location, crews are still in corridor enabling works, land clearance, archaeological mitigation, and utilities relocation. In another, earthworks are already advanced. Placing and compacting embankment, fill-in layers, building frost-resistant subgrade, and installing longitudinal drainage so the formation stays stable through spring thaw and heavy rain. Where the alignment crosses rivers and highways, bridge structures and viaduct piers are often the progress markers because they require long lead times for foundations, formwork cycles, and staged traffic management. February work in the Baltics has a seasonal rhythm. Heavy earth moving can continue where ground conditions allow, but the critical winter tasks often concentrate on structural works, precast production, and indoor station packages. That can mean piling and pier construction for major viaducts, fabrication of steel spans, and ongoing casting of precast elements that will be erected quickly when weather windows open. It also means pushing forward detailed design, procurement, and early installation of railway systems that can be staged ahead of track laying, such as cable ducts, equipment rooms, and substation platforms. Across the rest of 2026, the program tends to accelerate into long linear production. That is when large sections transition from formation to railway, with the placement of sub-ballast and ballast, installation of sleepers, rail strings, and continuous welded rail stressing. Parallel teams build the electrification, mast foundations, portal structures, contact wire, and return current systems. Signaling and telecom installation follows, with line-side cabinets, fiber runs, and the interfaces needed for modern train control, then repeated testing as each segment becomes energizable and ready for commissioning. Stations and terminals are their own mega projects within the mega project. City centre works typically focus on track reconfiguration, platform construction, passenger concourses, accessibility systems, and interchanges with buses and trams, while freight terminals focus on yard geometry, crane pads, and customs-ready circulation. Through 2026, the schedule pressure usually sits on stitching these nodes to the main line, so early operational segments are meaningful, not isolated track. Under the Hudson River, between New Jersey and Midtown Manhattan, the Hudson Tunnel project is the core rail element of the Gateway program. A new two-track crossing and then fully rehabilitate the aging North River Tunnel that carries most Amtrak and NJ Transit trains into New York Penn Station. The new build is typically described as roughly 9 miles of new tunnel and related works, when the approach structures are included, with 2 new single-track tubes under the river designed for modern safety standards, ventilation, fire life safety systems, and higher reliability for the busiest rail bottleneck in the United States. The construction is split into enabling works, river tunnels, Manhattan and New Jersey approaches, and the later rehabilitation of the existing tunnel. The reason it is staged is operational reality. The current tunnel must keep carrying peak hour traffic while a replacement is built beside it. That drives sequencing, work windows, and a build new first, then take old out of service one tube at a time plan. By February 2026, the project is in the period where the early civil packages have already reshaped the job site, and the heavy underground work is the headline activity. In New Jersey, that means continued excavation and structural build-out for the portal area and approach cut and cover sections, plus the completion of support of excavation walls, cross-lot bracing, and utility relocations that clear the way for the tunnel alignment to dive underground. On the Manhattan side, February work is dominated by deep excavation and structural concrete for access shafts and underground launch infrastructure, because tunnel boring in dense urban ground depends on stable shafts, slurry treatment, and muck handling, and robust ground support. Across 2026, tunnel boring becomes the production engine. Tunnel boring machines typically advance in carefully controlled rings, with precast concrete segments erected immediately behind the cutter head, gaskets compressed at each joint, and grout injected to stabilize the annular space. In February, the work is often about maintaining uninterrupted TBM logistics, segment delivery, spoil removal, ventilation duct extension, water management, and continuous surveying to keep the alignment within tight tolerances as the machines pass under the river and adjacent infrastructure. The systems tunnel comes next, and it overlaps with excavation rather than waiting for final breakthrough. As soon as stretches are structurally complete and dry, crews begin installing walkways, cable trays, drainage lines, emergency egress features, and the backbone power and communications conduits. Over the rest of 2026, that interior scope expands into ventilation equipment, lighting, fire detection, and suppression interfaces, and the civil finishes needed for maintainable, code-compliant operation. Track work is later in the sequence, but the tunnel must be built with the precise geometry and clearances that make track and electrification installation straightforward. A major parallel construction stream is the surface and subsurface integration at each end, tie-ins to existing right-of-way, protection of adjacent utilities, and construction of structures that allow trains to transition from new tunnel to existing tracks without bottlenecks. Through 2026, the project is also building the documentation and testing pathway for certification, because underground rail commissioning is as much about proof of performance as it is about pouring concrete. Cutting straight through Sydney's densest growth corridor, Sydney Metro West is being built as a new, fully segregated, high-frequency, rapid transit line linking the CBD at Hunter Street to Westmead, with intermediate stations that anchor Parramatta and the Inner West. The core section is typically described as about 24 kilometres of new metro railway, largely underground, designed for high-capacity operations, with modern platform, screen doors, advanced signalling, and stations built for fast passenger circulation. The engineering story is dominated by tunnelling and stations because the alignment runs under established suburbs, major roads, and existing rail and utility corridors. Most of the route is bored twin tunnels, with cross passages at intervals for safety and maintenance, and large mined or cut and cover station boxes where trains stop and passengers transfer. Every station is effectively its own mega project. Deep excavation, retaining walls, temporary decking to keep streets open, and multi-level structural frames that must accommodate ventilation, power rooms, and concourses. By February 2026, the program is typically in a phase where multiple tunnel drives are either complete or nearing completion, and station construction becomes the visible schedule driver. February work at key sites commonly includes continuing deep excavation and base slab pours in station boxes, progressing through staged levels of structural concrete for platforms and concourses, and installing permanent access, shafts and ventilation structures. Where tunnelling is still active, February is usually focused on maintaining TBM productivity, segment deliveries, spoil handling, dewatering, and continuous settlement monitoring to protect buildings and utilities above. Across the rest of 2026, the project shifts from civil to railway. In practical terms, that means completed tunnel sections transition into track slab construction, installation of rails and fasteners, and the start of systems fit out. Power distribution expands with substations, high voltage feeders, and low voltage station services. Communications and control rooms take shape with fiber backbones, radio systems, CCTV, passenger information displays, and network integration that supports both operations and safety. Ventilation fans, smoke control dampers, and fire-rated linings are installed and tested as permanent systems, not temporary construction ventilation. Station architecture advances in parallel because metro openings are often constrained by fit-out and commissioning rather than tunneling. Through 2026, stations move into waterproofing, wall and ceiling finishes, lifts and escalators, platform screen door installation, and the back-of-house spaces that allow staff and emergency responders to operate the line. Above ground, each station typically includes precinct works, new public plazas, bus interchange areas, road realignments, and utility reinstatement, all staged to keep traffic and local access functioning during construction. The line's performance depends on systems integration, so 2026 also includes the early commissioning pathway, progressively energizing electrical zones, validating signaling interfaces, and running test trains on completed sections as soon as the civil works, track, and protection systems allow. That testing is iterative, with software tuning and safety case documentation running alongside physical installation. Well south of central Dubai, in the Dubai South District, Al-Maktoum International Airport, often referred to as DWC, is being expanded into a long-horizon aviation hub intended to take over the bulk of the Emirates' passenger and cargo growth. The expansion is planned as a multi-decade build-out with staged capacity increases. Commonly discussed, in terms of ultimate throughput on the order of 200 million passengers per year and extremely large cargo volumes, supported by a vast airfield and multiple terminal complexes. The scale is defined first by the airfield. DWC's master planning has long centered on multiple parallel runways and extensive taxiway networks, because the limiting factor at mega hubs is not only terminal processing, but also the number of independent takeoffs and landings that can be sustained in peak hours. That requires enormous pavement quantities, high-capacity airfield lighting and power, and a stormwater system sized for rare but intense desert downpours. The terminal side is equally large, with concourses designed to handle wide-body fleets, high gate counts, and long transfer flows, plus landside road systems that function like a small city's highway grid. By February 2026, the expansion work is typically organized around enabling packages that transform the site into a construction-ready platform for terminals and runways. February activity in a program like this centers on earthworks, grading, and ground improvement across large plots, because any differential settlement becomes a long-term operational risk under pavements and terminal foundations. At the same time, crews push underground utilities, potable water, firewater rings, sewer and drainage, district cooling corridors, and high-voltage substations with redundant feeders. These networks are built early because every later structure depends on them, and because long-lead procurement for electrical gear and pumping systems can dominate schedule risk. Across the rest of 2026, the project typically transitions from horizontal preparation into vertical construction on priority assets. That includes starting or expanding terminal substructures with deep foundations and pile caps, then moving into concrete cores, long-span roof steel, and facade systems designed to manage heat gain. For airside, the year's work often includes building new taxiways and aprons in sections, placing stabilized base layers, then completing asphalt or concrete surfacing with tight tolerances for drainage and aircraft loading. Airfield electrical advances in parallel, with duct banks, cable pools, light bases, signage, and the control systems that ultimately connect to the tower and airfield maintenance facilities. Cargo and logistics elements are usually pulled forward because they can generate early operational value. In 2026, that can mean expanding warehousing footprints, building truck staging and customs areas, and installing high-capacity power and data infrastructure for automated handling, screening, and temperature-controlled supply chains. Support facilities, maintenance hangars, GSE yards, fuel farms, fire and rescue stations, and accommodation or administration buildings often proceed as separate packages so that the airport can be commissioned in operational blocks, rather than waiting for a single all-at-once completion. On the Somerset coast, near Bridgewater, Hinkley Point C is being built as a twin-reactor nuclear station using the EPR design, intended to add about 3.2 gigawatts of low-carbon baseload generation to the UK grid. The plant is laid out as two near-identical nuclear units, each with its own reactor building, turbine hall systems, safety auxiliaries, and a shared set of site-wide services, including cooling water intake and outfall structures built to operate reliably in a harsh marine environment. The construction sequence is defined by nuclear quality requirements and the logic of heavy lifts. Early civil works created the platforms, seawalls, and deep foundations. Then the program moved into massive, reinforced concrete structures for the nuclear island. The reactor buildings rely on thick base mats, densely reinforced walls, and multi-layer containment with embedded steel liners, penetrations, and anchorage points that must be placed to millimeter tolerances before concrete pours can close them in. That drives a hold point culture where inspections, traceability, and testing are scheduled as critical path activities. By February 2026, Hinkley Point C is typically in a mature build stage where structural works remain active, but systems installation and commissioning preparation increasingly dominate. In the reactor buildings, February work commonly includes continuing assembly and installation of large modular steel and mechanical components, progressing internal concrete structures, and completing containment-related works that enable later pressure testing. In parallel, the turbine halls advance through steel, erection, crane runway completion, and mechanical installation zones for condensers, feedwater systems, and auxiliary skids, because conventional island progress must keep pace with the nuclear island to avoid later bottlenecks. A defining 2026 theme is the transition from civil first to systems first. Over the year, crews push high-integrity piping installation, valve packs, cable tray networks, and instrumentation routes, then follow with cable pulling, termination, and functional checks. Ventilation systems, filtered air trains, and safety-related cooling circuits are installed with strict cleanliness controls and documentation trails. Temporary construction power and logistics progressively hand over to permanent electrical distribution, including large transformers, switchgear, and redundant supplies that support nuclear safety classifications. The site's marine works remain central in 2026 because the station depends on reliable cooling water infrastructure. That includes ongoing completion and protection works on intake tunnels or culverts, pumping stations, screens, and outfalls, plus erosion and corrosion protection in the tidal zone. Civil works also continue on waste handling and maintenance buildings, access roads, and the on-site batching and precast logistics that keep high-volume concrete operations consistent.